In this video, we apply the same principles based on energy, but now to look at lateral torsional buckling of a beam. We were looking at column buckling before. So you've likely seen in the design of steel structures that if the compression side of a beam is not properly restrained out of plane, it could undergo lateral torsional buckling. So here is a simple picture demonstrating the idea of lateral torsional buckling. So just like with column buckling, we will explore beam lateral torsional buckling also with a simple discrete approximation. This discrete approximation consists of a rigid plate that is supported by a spring that resists torsion and another spring that resists out of plane bending. The torsion spring constant we'll call K sub T, and the out of plane bending spring constant we'll call K sub B. We'll ignore deflections in plane. We'll ignore deflections due to in-plane bending because those deflections are much smaller than the deflections due to lateral torsional buckling. So first, let's look at kinematics. We'll look at an equilibrium configuration in which there is some out-of-plane deflection. Just like we looked at an equilibrium, a non-vertical equilibrium configuration in the case of a column. Here we'll look at an equilibrium configuration that has an out-of-plane deflection. So it's easiest to visualize such a deflection by looking at it down the x-axis in a front view. So the undeformed position is like that. After out-of-plane bending, it becomes like that. And then after the twist, the final configuration looks like that. The sequence of rotations, first bending, then twist, is important because recall from one of the previous videos that rotations in 3D do not commute. So we have to be careful in what direction, in what sequence we apply them. So let the angle of bending, which is rotation about the z-axis, be theta, and the angle of torsion, which is about the x-axis, be phi. And let's see how we can construct the rotation matrices corresponding to torsion and bending. So if we recall from our study of rotation matrices 2 assignments ago, we remember that we can build a rotation matrix by asking what the rotation does to the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. So let's look at rotation about the z-axis by an angle theta, which is bending. So 1, 0, 0 is taken to cosine theta sine theta 0, and 0, 1, 0 is taken to minus sine theta cosine theta 0. Therefore, the rotation matrix corresponding to bending, which we'll call R bend, is cosine theta sine theta 0, minus sine theta cosine theta 0, and 0, 0, 1. 0, 0, 1 is just the z-axis. It's kept intact by the rotation. Similarly, the rotation of phi about the x-axis, which is torsion, can be constructed in this way, which we'll call R torsion. Now, the position vector of the load in the undeformed configuration is simply L00. The x component is L, and the length of the beam is L. The position vector of the load in the buckled configuration is we have to apply these two rotations in that sequence to the undeformed position vector. So R twist times R bend times L. So we're applying R bend first and then R torsion. So the Z component of the position vector of the load we can get by simply dotting with the unit vector in the Z direction, which is 0, 0, 1. And we just get L times sine phi times sine theta. So the energy is the energy stored in the springs, which is 1/2 k theta kt phi squared plus 1/2 k v theta squared, plus the load times the height of the load, weight times the height. So that is the total energy.